This is the first of the 9.3.4 videos on Bronsted-Lowry theory. Now you've got two options for these videos. First of all, you can watch them and treat them like a lecture and just copy in the notes that are usually in grey as you go, or I've actually got these notes in Schoolbox. They're called 9.3.4 notes.pdf, and they've actually got the grey notes mostly in there, so there'll be less copying out. It depends on what is best for you as far as education goes though. If you like listening to lectures, listening to explanations and writing stuff in helps you remember things, then please do that. Otherwise, just have the notes printed out in front of you so you can go through them as we go through them. I'm going to break this up into a few videos so they're shorter, so it'll be easy to digest rather than one big long video. And in addition, at the bottom right hand corner of each page, I've got 3Q. That's a guide to the person whose week this is to write questions, how many big ideas are on this page. But you don't have to wait for someone else to write questions. A good way to study is, particularly if this is just me talking at you and you reading notes, is that if you want to learn this stuff properly and actually understand what's going on, this is a guide to how many big ideas are on this page. There's 3 big ideas on this page. You should be able to write 3 points or 3 notes or 3 questions for yourself off this page to remind you what are the key ideas from this page. So let's start Bronsted-Lowry theory. The first thing is, Bronsted-Lowry basically said that an acid is a proton donor and a base is a proton acceptor, and that's critical for this course because from now on, that is our definition of what an acid and base is. An acid is a proton donor and a base is a proton acceptor. But according to the Bronsted-Lowry theory, whether something is an acid or a base depends on 2 things. It depends on the properties of the substance itself and its properties relative to the solvent, i.e. whether it will actually accept or donate protons from a solvent. For example, HCl, hydrogen chloride gas itself, is not really an acid or a base, but when you put it in water, it will donate protons to water. So HCl in water acts as an acid. And that's why Bronsted-Lowry theory is important. It recognises the importance of the solvent. Things are acids if they donate protons to the solvent, and things are bases if they accept protons from the solvents. That's the big change in acid-base theory when it came to Bronsted-Lowry theory. It didn't require water, even though most acids and base reactions are in water, but it explained what water did in relation to acids and bases. So what's a Bronsted-Lowry acid? And simply, if a substance, let's call it HA, has a greater tendency to give up protons in the solvent, then in that solvent, the substance will be an acid. So what it means is in that solvent, because it wants to give up protons more than the solvent does, it will give protons to the solvent and therefore will act as an acid in that solvent. So for example, if HA has greater tendency to give up hydrogen ions than water, then when you mix HA and water together, something's going to happen. Here's a good chance to pause the video if you wish and see if you can write down the equation for this. So pause now. Okay, let's see what happens when HA is added to H2O. It wants to give protons to the water, so it turns into A- plus H3O plus, and a good way to show this is actually show that proton transfer. We can show the hydrogen ions being donated from the HA to the H2O, forming A- and H3O plus, i.e. HA acts as an acid in water. So let's just have a quick look at this though. There's 3 ideas on this page. I would say the big ideas are what an acid and a base actually are, what Bronsted-Lowry theory said about the role of the solvent, and what does it mean for something to be a Bronsted-Lowry acid. So there's 3 big ideas on this particular page. Moving on, Bronsted-Lowry bases. Now if a substance B has greater tendency to accept protons in the solvent, then in that solvent the substance will be a base. What that means is because it's got greater tendency to accept protons, it will accept protons from the solvent. So for example here, if B has a greater tendency to accept protons than water, then pause the video, have a go, let's see what happens. Okay, so if B has got a greater tendency to accept protons than water in this case, then it will accept protons from water. So in this case, the water will actually donate protons to the B, producing Hb plus and hydroxide ions. So that means that B acts as a base in water, in that particular solvent, water. Which leads on to the next thing, which is Bronsted-Lowry conjugate pairs. When an acid gives up a proton, it forms what's called the conjugate base, i.e. the conjugate base has 1 less proton than the acid. So for example, acid plus water, well we know when you put an acid in water, being an acid, by definition it's going to give protons to the water. That means that acid has lost a proton. So what happens is when it loses a proton, it's going to form, well water's going to form H3O plus. What's going to be left behind is the acid, which has 1 less proton, is called the conjugate base. And the reason it's called the conjugate base is because in theory, what can happen is that base could accept a hydrogen ion back from the water again, and that means the reaction could go back that way, particularly if it's a weak acid and a weak base, or weak conjugate base situation. So it's called the conjugate base. It's got the potential to reaccept protons. So let's just get rid of that so it makes it a bit more clear. The basic idea though, an acid gives a proton to the water turns to hydronium, and what's left behind is this acid with one less proton is now the conjugate base of that acid. So let's look at a few examples here. It says all cases below, box the acid and underline the conjugate base. So I'm going to look at this example here. We're going to say, okay, I've got HA plus H2O goes to A minus plus H3O plus. Obviously HA has donated a proton to the water, and it says here box the acid. Okay, that means HA must be the acid because it's the thing that's donating the protons, and underline the conjugate base. What does HA become once it's lost the hydrogen ion? Well, here it is. This species here has one less hydrogen. That's what it's become. So in this situation here, HA is the acid and A minus the conjugate base. But why is A minus a base? Well, it's because it's possible that that A minus could react with H3O plus. It could accept that proton back from H3O plus, therefore acting as a base, a proton acceptor, to turn back into HA plus H2O. So these examples here are for you to try yourselves, to try and see if you can figure out what happens in these situations. Box the acid and underline the conjugate base. And there's two ideas here. I think the big idea is what is a Bronsted-Lowry base, and what does it mean to be a conjugate acid or a conjugate base. Okay, third page here in the last of this video. Similar situation, when a base accepts a proton, it forms what's called the conjugate acid. The conjugate acid has one more hydrogen ion than the base because the base has accepted a hydrogen ion. So here we have base plus water. Let's get rid of this out of the way. Base plus water. When a base accepts a proton from the water, well, the water is going to turn to hydroxide ions, which we typically associate with bases, but now this base chemical is going to have one more hydrogen ion, so therefore it could then donate that again later on, so this becomes a conjugate acid. So down here, in all cases below, box the base and underline the conjugate acid. Well, in this case here, the water has donated a proton to be our base, therefore our base has become this thing called BH plus OH minus. So this is accepting the proton, therefore in this case this must be the base. This is what it's become, this species with one more hydrogen ion. This is the conjugate acid, because in theory, as it shows over here, this new species, BH plus, it could donate a proton back to the hydroxide ion again, depending on how strong or weak this original base B was. And therefore, because this species BH plus can donate protons, it's technically an acid, and we call it the conjugate acid of this base B. So here's some more examples for you to practice with, to see if you understand the whole idea of conjugate acids and conjugate bases. So last but not least, conjugates. An acid and its conjugate base, or a base and its conjugate acid, together are known as a conjugate pair. And there's two big ideas on this page. There it is, what is meant to be a conjugate acid, and what is a conjugate pair.